Greetings, statics class. This is the beginning of chapter 9. So we did some things in chapter 5 that looked at center of mass. We're going to revisit some of that and we're going to add to it. So this has to do with distributed forces, moments of inertia. I'm going to start with just some definitions. Sometimes that's helpful. Defining some variables over here. So we have delta F, which are distributed forces. Delta A, area of an element. R, as it has been all semester, an R vector is a resultant. Q sub x is the first moment of an area, and it would be with respect to x. The x-axis. Because of course we remember when we talked about area and distributed and where is the center of mass, it depended on which direction you were. It was a point in space. We're going to talk about I sub x. So this is a moment. So this is the first moment. This is the moment of inertia. That's a fun word. Inertia. It's also the second moment. We don't usually call it that, but it's the second moment with respect to the x-axis. Okay, and I know you may not be able to see this. We'll cover them on the screen, but I just wanted to capture a few as we got started. J sub O, this is a polar moment of inertia. Think polar coordinates. And the O, the J sub O, is about sun origin. And if I thought about delta F over delta A, that's the magnitude of a force over a particular area. Okay, so just some little variables to get us started. All right, so we've talked about distributed forces that were proportional over some sort of area or volume. We would do some summing or integrating. Sometimes we did it, summing the areas, we make charts, add those up. The first moment of the resultant about any axis was determined by doing the first moment of the area about that axis. Remember, that was Q. And we're going to talk about forces that are both proportional to area or volume and also very linearly from the distance, with distance from a given axis. We'll see that the magnitude of the resultant depends on the first moment of the force distribution with respect to the axis, and the point of application of the resultant depends on the second moment. So we're going to talk about the second moment, or really it's more commonly called the moment of inertia. So moment of inertia of an area, and I apologize, I meant to fix this slide and I didn't get that done. This should be a delta F. This should be, this is P times delta A. So these big P or big D's are typically a delta, which again has to do with this small little area and the force at that exact area. Okay, so we have gamma, and unfortunately it's substituted G for gamma. So gamma times Y times delta A. So the force is think of it as mass, right? So specific gravity, which is gamma, leads us to mass. So the specific gravity times some distance times that area. As I walk down, I eventually get to the fact that the moment around X is this gamma times, that is supposed to be an integration symbol, gamma times the integration symbol y squared dA. Now, what's interesting is Q was some sort of, and here it is written out properly. I don't know what happens here, but it does happen. Q, which is the first moment of an area, or the first moment of inertia, is some sort of linear unit like inches or meters or millimeters to the third power. But moment of inertia, this I, is going to be something to the fourth power. So for instance, this is meters to the third power. This is meters to the fourth power, or feet, or inches, or whatever unit is appropriate. All right, so as I calculate these, so the moment of inertia with respect to the x-axis, again, this should be an integration symbol. I'm not sure what that is supposed to be. Makes me want to say away is what it makes me want to say. This first moment of inertia with respect to the x-axis, first moment of inertia with respect to the y-axis. What you'll notice is, if I'm referencing the x-axis, I have the y distance, right? Probably easiest to see on this first diagram. So my distance y is how far away I am from the x-axis times whatever that little area is. In this case, in this picture, it would be dx times dy. That would be my area. So if you remember back to chapter 5, where we computed areas of slices like this, so this kind of a slice that goes sideways is the width is dy, but the length is whatever a is minus x. So this expression for area is a minus x times dy. This area is dx times whatever the height is. This area is going to be, because this is a rectangle, it is always going to be b. And then it's dy. Okay? So the nice thing about this is a nice well-behaved rectangle. Probably wouldn't have to integrate there. I could probably do that algebraically. If I look at this piece, my width is dx, and my height is dy. And again, you have to think about, am I referencing my x-axis, or am I referencing my y-axis, right? And why is this important? Well, it depends on what kind of a shape I'm trying to do, and how is it going to be used, okay? So am I trying to stop movement based on the x direction or based on the y direction, okay? So the fact that this is squared, this distance is squared, is huge. So that distance away from the x-axis happens to be what is the most important thing. In this case, if I was looking at the y-axis, the distance away in the x direction, again, let me point to this one. If this is my y-axis and my distance away in the x direction, that's what's going to dictate how this thing is going to perform, all right? And I do want to mention, I posted a video that was made by somebody from Texas University, and he does a really good job of talking about the concepts behind it. But I wanted to go through some of the application side. We're already familiar with picking these little thin strips. Again, this is very similar to what we did back in chapter 5. If I referenced this rectangle over here, I sub x is going to be my moment of inertia with respect to x. It's the y distance, so that's my y squared, times this area. So what is this area? Well, it's dy times b, because b is that width. So I have y squared times b what I find is I integrate from 0 to h, so I integrate from 0 to h. When I do this integration, evaluated at its limits, I find that it's 1/3 the base times the height cubed. Now, there's a chart that you will find in your book that will give you many of these common shapes and their moment of inertia. Okay, they're very helpful. We can also look in other directions and do that same kind of analysis. All right, polar moment of inertias. Okay, so recollect that in polar moment of inertias, I have an angle and I have a radius. Okay, so that's how I describe areas. For certain types of shapes, polar moment of inertia is very helpful. So my polar moment of inertia is r squared, integrating r squared times dA. So some sort of distance, so think position vector, way back we talked about position vectors, and then dA. So what is that area? Well, that little area is simply x times y, but we'll get there, hang on. But what is r? Well, think Pythagorean theorem. It is x squared plus y squared. That gives me r squared, right? Think circles. When I integrate this, I can break it into two pieces. So I have x squared dA plus y squared dA. I still need to integrate it. What's interesting is polar moment of inertia is actually the moment of inertia with respect to the y-axis plus the moment of inertia with respect to the x-axis. Okay? So that's a very important relationship there. Did I write that down? Let me add that. I don't know if you can see that over here. J naught equal, it's actually J sub O Ix plus Iy. So sometimes it's easier to figure it one way, sometimes it's easier to figure it another way. Now this radius of gyration, okay, so think about taking a strip and revolving it about an axis to create some sort of shape. So if we have an area A with a moment of inertia I sub x, so again, we're referencing the x-axis when we say I sub x. Imagine that the area is concentrated in a thin strip. So I take this whole area and I concentrate it in this thin strip so that I can do some calculation. I have an interesting tactic here. So my moment of inertia with respect to x is this k squared. So where does k come from? That has to do with how far away, if I were to concentrate this, how far away would I have k, all right? In most cases, you're not given this unless the problem just happens to. But as we do our analysis, when we find our moment of inertia with respect to x-axis, and we can find our area, then we can find k squared, okay? And that's what this formula shows us, that k squared is the square root of I sub x over a. So again, it allows me, we haven't gotten there yet, so don't worry, but it allows me to do that. If I were to do, so k sub x is with respect to the x-axis, I have k sub y with respect to the y-axis. Okay, let me say it one more time. The moment of inertia depends on which axis we're referencing. If we have a shape, it depends on how far away it is. It depends on which axis we're referencing. The distance to x and the distance to y are probably different. So we see the same relationship whether we're referencing x or whether we're referencing y. I have a polar moment of inertia. With a polar moment of inertia, you end up with a circular ring. So I have that same radius of gyration. And again, typically you would know the polar moment of inertia or be able to look it up, figure out the area, and then solve for this radius of gyration. Again, we'll use that in some other calculations. Just like my polar moment of inertia, my polar moment of inertia, my radius of gyration squared. Again, think circles, right? The overall radius is the radius squared, the x component squared, and the y component squared. Kind of cool, huh? Think about the formula for a circle. All right, so let's jump into a sample problem. I'm going to take a drink of water. So we have a triangle, and we want to find the moment of inertia with respect to the base, okay? So we're going to do this problem, and then the formula for this is actually in that chart I referenced. To find the moment of inertia with respect to the base, sometimes it depends on which direction we're referencing. In this case, it says with its base, so this is the x-axis. So we draw a triangle. We have this base B and height h. What we're going to do is use similar triangles, right? Similar triangles are pretty powerful. So the height of this overall triangle is h. The height of this little triangle is h minus y, right? If y is whatever is the middle of this strip, then y value is going to continue to change. So I have h minus y. And the portions, all the portions of the strip are the same distance from x. So this strip right here, whatever strip, it's parallel to the base. So that's where that comes from. So again, we're doing similar triangles. So my derivative of the moment of inertia with respect to the x-axis is equal to y squared times dA, right? And that comes from one of those formulas. It had the integration symbol on the other side. So if we integrated both sides, we'd get back to that formula I showed a minute ago. And we have to find the area of this strip. So let's do that. Da-da-da. So my area for this strip is whatever the base is times h minus y over h. So where do those come from? Again, this is a ratio, right? So the height is the overall height. Here is the base, okay? So here's this ratio. The base over the height is going to be equal to the height over dy, or times dy. So this h minus y, that has a relationship with L, okay? So length versus the base, okay? And then h minus y over h. So again, where do those come from? Here's the base. Here's the length of the little triangle's base. They're calling that L. So that's that ratio. The height of the big triangle has to be in the same position as the base. And then the height of the little triangle, which is h minus y. They solve for L, and then they substitute so that we actually get that last piece where it says the area of this strip, right? The area of that little strip is the base times h minus y over h times dy. So if I integrate from y equals 0 to y equals h, why did I pick those limits? Because this whole triangle goes from 0 to h. Whoops, I went the wrong way. So when I go from 0 to h, that moment of inertia with respect to the x-axis, again, is y squared times dA. That's a given formula that you need to kind of commit to memory. It's okay if you have it on a formula sheet, but you need to lock that one up. We're going to integrate from 0 to h. So I have y squared times, what was dA? That was that thing we just calculated a minute ago. So that's this piece right here. I'm going to substitute that in, do my actual integration, and I come up with the base over height is let me finish. We'll apply the limits, and then I sub x is base times height cube over 12. Again, that value for a triangle would be found in your chart. And I have all of those charts in a file, in a document on Canvas. So if you just look, you'll see that. Now let's look at polar moment of inertia. So we want to find the centroid polar moment of inertia of a circular area by direct integration. We're going to, then the second part is determine the moment of inertia of a circular area with respect to the diameter of the area. So since this area is circular, I would like to use polar moment of inertia. My polar moment of inertia, I'm going to use radius, right? So it's radius squared times dA, that's my formula. And you may say, well, where did that u come from? Well, the overall radius of this whole circle is r, but my location, I'm just going to use u. You could call it whatever you want it, but they're just using u to indicate this location as this little circle moves out, 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 and out. So my polar moment of inertia is going to be the radius squared times dA. So what is dA? What is the area of this circle, right? Well, 2 pi r du, because the thickness is du. So the location, right? My location is u times d. So again, that's going to continue to change. So you always got to think of when are you putting in a du or a dA? Well, when that location of this strip is going to change as it moves out to the edge of the circle. So my polar moment of inertia is the derivative of that piece, or integrating dj sub o. Substitute all those pieces in. U squared, I'll just use that u, because again, the u is the location, right? It's the height, or whatever the x or the y you normally think of. And then dA, I substitute that in. Pull out the constant, do my integration, evaluate the polar moment of inertia with respect to this origin is going to be, I think that's a wrong letter there, something over 2. That should be something else. That should be I think that's pi. I think that's supposed to be a pi. That's what that p is. And then the radius to the 4th power. Again, that's in the chart in the back of your book. Or it's in the chapter, but it's also in the back of your book. And it's posted on Canvas. All right, because, so let's look at, for the sake of the circle, x and y will be the same, right? They're going to be symmetrical. So that's what that first statement is saying. So I could do moment of inertia with respect to x, moment of inertia with respect to y for a circle, but really polar makes more sense, truthfully. So my two polar, or my I sub y and I sub x are going to be equal because that circle is nicely centered in the middle, so it's going to be the same no matter which direction you go. My polar moment of inertia, again, this is a formula to remember. I sub x, I sub y, you could just replace that and say it's 2I sub x. I do that calculation and come up with the same answer as I came up with doing it with the polar moment of inertia. Symmetry is always good, is what that's saying. All right, I am going to stop there because I wanted to stop with when we got to 9.2.